Good morning, everybody. So, we're going to be talking about energy and orbits today. And because I'm a little bored, uh, you're going to be forced to see me. Good times, good times. All right, we're going to cut right to it today. So, let's start with a little discussion about um, dealing with issues regarding center of mass. I had a few people come online last night for tutoring and wanted to ask some questions. So here's a straightforward example of what has been on the AP exam in the past. Imagine two objects. I don't know. It could be a star, a binary star system, or I don't know, two equally massed objects that just be hanging out in space, separated by a distance r, that are in a circular orbit about each other, which means that they, something like, let's say it's circular, so there you go. So they're traveling along this circular, path. It's not perfect, but I'm trying. Make it a little more perfect. There we go. So in this example, with them traveling in a circle, like so, the real question comes down to how do we treat this problem different than, say, other problems where we didn't have to deal with the center of mass. This one is a clear center of mass problem. I think we can all agree, if they have the same mass, that the center of mass is in their middle. A student last night said, are there any new equations? Well, there is. There's a new equation, and it's only this one. Everything else we've been using so far is something we've already known, but it's combining them all and understanding what each piece means. So remember, we're using net force equals ma to combine everything together. There's a single force that's acting on our planet. It is the force of gravity. It just so happens it acts on both planets, Newton's third law. Now, in addition to that, there's the fact that they're traveling in a circle sometimes. So if they're traveling in a circle, we have centripetal acceleration. And in addition to that, if we're talking about timing them, since we know they're traveling at a constant velocity, then we are able to figure out, how long it's going to take for them to go around once, because we have access to distance over time. These are the only things we're dealing with. The only one that's new in this unit is this one. But yeah, we are combining them together. This r is not a radius, it is the separation distance. Yes, sometimes it is the same as the radius, but you have to really pay attention. This r is the radius of curvature. This r is the radius of a circle. Probably these two are always going to be the same, but they don't have to be the same as that one. So in this example, they're not. In fact, I think we can agree that the radius of curvature is going to be 1/2 the separation distance, because I think the center of mass is in the middle. Now, I didn't have to do any fancy center of mass calculations, but if you'd like, we could. We could say that this planet is 0, and the distance to the center of mass would be m times 0 plus m times r, all divided by m plus m, or 2m. So doing a little bit of math here, I get mr over 2m, or r over 2. So see, we could use the center of mass formula. I just didn't, because I didn't want to, didn't have to. So if I wanted to know how long it takes this system to orbit, I'm searching for this. So yeah, it's like massive substitution. Let's give it a try. Starting with net force equals mac. and that will be m times g over r squared equals m v squared over 1/2 r. I'm just doing all the sub. You need to be paying attention and going through this with me. So I can do a little bit of math here. For example, I can multiply both sides by 2. That would get rid of that. I could get rid of one of the r's, and I can get rid of one of the m's, and I'm left with 2mg over r equals v squared. Just doing the problem. Let's see, I want t, so I can put that in there. So 2mg over r equals, looks like 2 pi, this r is 1/2 r, don't want to forget that, over t, but all of this is squared. 2 and the 1/2 go away. No big. I'm gonna have to square it to do anything else, and I am running out of room, so let's maybe bring all this up a little bit. There we go. Give me a little bit of room. We'll work right there. So 2m big G over r equals pi squared r squared over t squared. And now I'm going to cross multiply and get t squared equals, and I mean, if you want, I can leave everything together, but I have a reason to do what I'm going to do. I'm going to really just solve for t, so I'm going to cross multiply that over there and put that over in the denominator. I'm going to cross multiply that over there. Oh, I know it's a lot, but I can do algebra. You should be able to. There. Now, I want to call your attention to something. If I just reorganize this a little bit, I get pi squared r squared times r over 2 over mg. I see I'm in the way, so there. Now, I'm putting this in here because notice we have r squared and the radius of curvature. This is what we would see if it hadn't been that the radius of curvature was just half of r. We'd have not r cubed like we saw before, we'd have an r squared for the separation distance and an r for the radius of curvature. That's what would happen. But this is an excellent example of the kind of question I think they could ask on the AP exam if they're trying to get you to deal with center of mass. This one's nice because it's neat, the center of mass being in the middle of the two of them makes it relatively easy to do mathematically. It's not terrible. But let's get to the real thing today. The real thing today is energy. To begin this discussion, I want to point out that some energy is always the same, kinetic. There's no need to make this a big deal. If something's moving, it has kinetic energy. If something's spinning, it has kinetic energy. It's really easy to see. The problem comes in the way in which we define potential energy, especially the way in which we defined gravitational potential energy. You see, we have been dealing with potential, I spelled potential wrong. We've been dealing with a shortcut, and it's unfortunate that we do it to you this way, but we have to. We've never really dealt with potential energy. We've dealt with a means of dealing with work when we are close to the surface of the Earth, and that's where mgh came from. But in truth, it's always supposed to have been mg h minus h naught, where h naught was the reference level. You should remember all the way back to first semester when we talked about the importance of the reference level. And this is no different. The reference level is something we set. Generally, we can deal with the lowest point in the problem. That's usually what we set. Find the lowest place the object can go, set that, make that your reference level, and that's what we've been doing. Also, mg. We've been using mg because the force of gravity near the surface of the Earth has been uniform. Well, there's two absolute problems with this. Our reference level is arbitrary. So the amount of energy we've actually been dealing with has never really been absolute. In fact, you're not going to like this, but what we've really been doing the whole time is saying there's always some gravitational potential and perhaps some kinetic. And as our object moves, the amount of energy flows between the two of them. We've been treating the potential energy as an absolute, that there is a place that we know of that is zero. And we've gotten things like, just subtracting from both sides, we get any change in potential gives us a change in kinetic. This is actually where mgh minus mgh naught comes from. It's always been like this. We've just not really highlighted it in this way. Gravity on a more galactic scale, or even a more solar system scale, or even just the Earth-Moon scale, gravity is different than this, actually. We describe being in what's called a gravity well, meaning that we're trapped on the Earth. The gravity is holding us here. If we want to escape the influence of gravity, there is no place on the Earth where we have zero gravitational potential energy. In fact, the definition should be that potential energy is based on whether or not you are interacting with the planet at all. That's what we call a universal standard for gravitational potential energy. That's going to be hard to understand, especially for the first time, but think of it like this. If you're on a planet, and most of you are, you're actually physically trapped on the planet. For you to escape the planet, meaning to get off the planet completely, you would need to go someplace far enough away where if you stopped moving, the planet couldn't just have you fall back. Meaning I could grab you and throw you into space. And for some of you, I'd probably like to do that. But I probably couldn't throw you far enough where you wouldn't just be pulled back down towards the Earth. Which means you've never really escaped the gravity of the Earth. This is why we call it a gravity well. Imagine an actual well. If the ground is, say, here, and one of you, not paying much attention, fell down the well, you might be trapped. Now, you could call your dog and say, "Timmy, I fell down the well, go get help." But truthfully, you're stuck in the well. To escape the well, you have to be lifted out of the well to get back to the surface. Now, this idea of gravitational potential energy is a little different than we've talked about. In this example, we would say being out here at the surface would be a gravitational potential energy of zero. We've brought you to the surface. And when you're trapped in the well, your energy is actually negative. That it takes a certain amount of energy to get you back out of the well. This is how we define gravitational potential energy in a universal setting. We define it as getting to a place where the gravity of an object no longer influences you. This is called setting the reference point at the standard location. I'm going to say this again because this is important. Setting the reference. At the standard location. It's a kind of an odd statement, but they'll use it in the problem. In fact, I've got a couple AP questions we're going to look at, and they use this in the course of their problem. Now, here's the issue. We get rid of the well here for a minute because the well makes for a nice example of if you're trapped in a well, it takes energy to get you out of the well. It's harder to see that when we're talking about a planet. So let's talk about a planet again. So here's our planet. And here's you. How do we, or where do we place you so that the planet is no longer influencing you, meaning you don't feel a force from the planet? Well, there's a little bit of mathy math here. So let's consider the force between the planet and you. And you take a pause for a minute. I got a text message. All right, back to work. So, how do I deal with the fact that gravity is based on a separation distance and two masses? The masses can't go to zero, clearly, but if I increase the separation distance, the force goes down. So how far away do I have to place you so that you no longer are experiencing the gravity from the planet? Technically, that occurs when r goes to infinity because you're always experiencing some. But this idea of infinity in physics is a little different than infinity in math. And generally in math, we tend to think that infinity means, infinitely far away. There's no way you can get there. In physics, it's different because getting you away from the Earth is actually not as hard as it sounds. You can escape the gravity of Earth. That's because there's other things in the solar system that also have mass. So for a lot of the times, our escape velocity is a little bit different, meaning how much energy you need to escape the planet. But ultimately, we base it on this idea that if you let r go to infinity, then that is the point where you are no longer experiencing the effects of the Earth. Now, here's where it's going to get a little bit more complicated. How do we figure out how much energy that actually is? This is going to be hard. We have to do work. That's where energy comes from. Work, by definition, is how much force you apply over a distance. So if I want to take you and move you from the Earth to infinity, well, how much work is done to take you and move you to infinity? Well, that normally I would say is just force times distance, but that assumes that times the cosine of the angle between them. However, our force is not constant. So we would have to do the integral. In this case, it would be the integral of the force of gravity dot dr, and then do that from, say, the radius of the Earth or any planet to infinity and beyond. So let's try it. And I am going to, because I'm not there in the classroom, I'm going to skip over some technical things here. But we're still going to do this calculation. So let's prepare. First, we're actually talking about the work done by the force of gravity, not the work done by us, meaning we're trying to work against gravity, so we are applying a force this way, but we're interested in how much energy there is in the gravitational force. So the gravitational force points towards the Earth, But we are going to try to move you, this is dr, away from the Earth. So we actually have a cosine of 180 degrees here that we will have to deal with. But again, I'm not going to make this hard, and I'm not going to deal with direction. Let's just figure out what the shape of this looks like. Here we go. Integral from radius to infinity of m for a planet, m for u, g over r squared dr. Now, this part's not terrible. All of this is a constant. So this equals mp, my, g, and now we have an integral of 1 over r squared dr from r to infinity. And this is a polynomial. You might not remember, but it is. When we think of our polynomial function, this is r to the negative 2. So we can use the polynomial rule on it because it's not r to the negative 1. So when we use the polynomial rule, we will get, well, first mp, my, g. Okay, we're taking the antiderivative. So we add 1 to the exponent, so it's now r to the negative 1, and we divide by the new exponent, so we divide by negative 1, and we evaluate this from r to infinity. How do we evaluate it from r to infinity? Well, it's not actually as hard as it sounds. Let's take this over here. Evaluate this from r to infinity. We're going to go mp, my, g, and this will be negative 1 over infinity minus negative 1 over r. Ta-da! This isn't very much, but let's do this. 1 over infinity is 0. Because 1 divided by any big number is 0, or very close to 0. So this just becomes mp, my, g over r. This is the work done in separating you from the planet. Now, technically, potential energy is always minus the work done by the force. So what we say is potential energy is minus mass 1, mass 2, g, divided by the separation distance. Now, I know this is a lot, but hear me out. Your equation sheet has this on it with the negative sign. The negative sign is there to indicate that you are trapped in a potential well, in a gravity well, so that when you are close to something that has a lot of gravity, you have negative potential energy. And to escape it, you want to add enough energy so that you go to 0 energy. That means you have escaped the effects of gravity and are now located way away from the object with a velocity of 0. That is escaping the object. You might not like this, but ultimately, if you want to be able to move past this oddity of it, then just understand the negative idea here, this negative gravity. It's not like you have, or this negative energy. It's not like you actually have negative or a deficit. We have just set the reference level in such a place that the energy is negative. Go back to the well. If I tell you that that where the clouds are and where the ground is and where the buildings are, if I had just set the reference level for all that was the stupidest looking cloud ever. Mr. Shelton trying to come up with the on-the-fly thing that you weren't going to talk about and always messes you up. Let's make a better cloud. Nice little puffy cloud. There. Now it looks like kind of like a caterpillar. Not a cloud. I don't know. No, it's still a cloud. This is my puffy cloud. No, I erased my puffy cloud. So there's my puffy cloud. Don't say anything. That's my cloud. Here is the ground. There's a door, chimney, smoke, you. Be careful, I'll throw you into space again. If we set the reference level here and say this is 0 for gravity, so this is h naught and it's 0, then all of our locations would have to be negative. We're below the reference level. It would never change any answer related to gravitational potential energy problems. I mean, imagine I drop something from here, which is 10 meters above my house, to here, which is, that's not going to work. Let's say that's 0. So let's say this distance is 10,000 meters, and here to here is 10,050 meters. This is negative 10,000 meters if that's 0, and this is negative 10,050 meters if that's the ground. If I want to figure out how fast something's going, if I drop it from there and it goes this distance, your math still works out to be the same. Up here we'd have gravitational potential energy. Down here we'd have gravitational and kinetic. It would be mg h plus no kinetic equals mg h plus kinetic. Oops. So mg 10,000 minus negative 10,050 equals k. Still ends up being mg times 50 equals k. But making everything negative doesn't change the problem. It just changes where the reference is. And that wasn't a great I was trying to do something really fast on the fly. What you have to understand, ultimately, is that we state that things that are trapped in a gravitational field will have a total amount of energy that is always negative until they escape it. Let me show you an example of how this actually would work. Let's say I actually do want to launch you off the planet. I'm done. And I think you need to leave. So I want to figure out how much kinetic energy would it take to launch you off the planet. Well, by our definition of gravitational potential energy, where the reference level has been set at infinity, to get you off the planet, I need to give you enough kinetic energy so that when I add your gravitational and your kinetic together, it equals 0. Meaning, I am going to give you enough velocity on the surface of the planet so that you make it all the way out of the gravity well, and at the point you're at the edge of the gravity well, you have 0 energy. That's the minimum amount of energy needed to kick you off the planet. So to do that, I would quite literally say, okay, so how much kinetic energy would I need? I would need this amount of kinetic energy. In fact, this has a name. This would be me giving you your escape velocity. The amount of energy you would have to escape the confines of the Earth. It's right there. You saw that for V escape, and that's called the escape velocity. Now, what this also means in practice is that generally a planet that is orbiting a sun or a satellite that is orbiting the Earth always has negative energy. Now this part's going to be a little bit tricky, but follow along. Let's pick a random planet. Planet X. Now let's do planet X, make them blue. With a satellite orbiting the planet. Mass of the planet, mass of the satellite, and let's say that the satellite is located a distance r away from the planet. And let's say that it is in a circular orbit about the planet. All right, so here we go. If it's in a circular orbit about the planet, we could figure out how much total kinetic energy it has, because we know how to figure out how fast it's going. Let's do that first. Let's figure out the energy in this orbit. So the total amount of kinetic energy would be based on the velocity, and we know how to get that. That would be first saying that the net force equals MAC, or mass of planet, mass of satellite, times G over R squared equals MV squared over, can I use the same R here? I think I can. A satellite is much smaller than a planet, and therefore it's safe to say the center of mass is at the center of the planet. This mass is the mass of the thing that's orbiting, so that's S. And now I can figure out how fast I'm going, but don't solve for V, solve for V squared. So I'm going to solve for V squared by canceling those out, cancel out one of the R's, and I get V squared equals MPG over R. Great. So how much kinetic energy does the satellite have? It has 1/2 mass of satellite times V squared, which is MPG over R. This is how much energy the satellite has in the form of kinetic. So we can write one more line. So we'll go MS MPG over 2R. Now it also has gravitational potential energy. It is trapped in a gravitational potential well. So how much gravitational potential energy does the satellite have? Well, just look it up on your equation sheet. You don't have to know very much here, but you do have to remember to use the negative sign. It'll be a massive planet, massive object, G over R. Now, here's the thing. The satellite's moving, and it's not moving slow, it's moving fast. But does it have enough energy to escape the Earth? And the answer is it doesn't. If we look closely, the total energy is still going to be negative. That'll be the sum of the gravitational plus the kinetic. So in this case, that sum is going to be mass of satellite, mass of planet, G over 2R, minus mass of planet, mass of satellite, G over R. If you get common denominators, let's put another color so people don't flip out. They're common denominators, put 2 on both, and I subtract, I find that my total energy is still minus MP MSG over 2R. Total energy is still going to be negative because you haven't escaped Earth's gravity. You've gotten something off of the Earth, you've gotten it traveling nice and fast and put it into a nice orbit, but you didn't escape Earth's gravity or the planet's gravity. You got it out into an orbit. It would need a lot more energy. In fact, what's funny is getting something, this is a circular orbit, and although it might not be clear, even if I made that orbit further away, I would still get this form, just R would get bigger. It's interesting here, but the thing to note that is when you're in orbit, you haven't even given yourself nearly enough energy. Apparently, it's only about half the amount of energy necessary to get out of the Earth's gravitational pull. And that's just to get you into a circular orbit. To get away from a planet takes a lot of energy. In fact, we didn't give anything enough energy to escape the solar system except 2 things, the Voyager 1 and 2 probes. And eventually, if we waited long enough, on a long enough time scale, they'd eventually just get close to something else and be pulled in by that object. or they would slow down to a stop and fall back towards the sun. The sun being the biggest thing here. Because think too, you can escape Earth's gravity, but there's still the sun out there. So when we talk about escape velocity, that's tough. And this is the basic idea, assuming there's only one object out there that you're trying to escape from. If you're trying to escape from more than one, it gets harder. So one more little thing here. I just want to bring this up because although I've been prattling on for a while, I like to always talk about some real things here. There is a point between the Earth and the Moon. And that point is special because at that point, the force of gravity on an object, say the Apollo spacecraft, is equally pulled in both directions at that point. Because you can find that there's got to be a place where the force between the mass of the planet, the mass of the satellite, and whatever this distance is, R1, would have to be equal to the mass of the moon times the mass of the satellite, G over R2. There's got to be a point where that's equal. Now, that's a special point because when we were launching things to go to the moon, we didn't have to get them all the way to the moon. We had to give them enough energy to make it to this point of inflection. We never gave them anything near the escape velocity. The rocket would have been so tremendously big that it would have been too dangerous to launch. As it was, the Saturn V was already pretty darn dangerous to launch. All right. I'm going to take a quick pause so I can show you what it is that I want you to do. All right, so here's what I'm thinking. I have posted this with this lesson. This is the first of 2 FRQs I want you to do. And they're it's not that they're hard, but they cover everything. So all the stuff. And so I know that that's probably going to make some of you a little bit crazy. I want you to try them. I'll be at tutoring tonight. There'll probably be a bunch of you there. It's okay. I'm happy to walk through these live with you. But make a reasonable attempt. Spend 20, 30 minutes on them first and then come to tutoring. If you look at this one, I want to point out question A. The total mechanical energy of the spacecraft, assuming the gravitational potential energy is 0 at an infinite distance from the Earth. So they say it pretty clearly what they want. This one is similar, except that in the case of this one, they want you to write the definition and the integral necessary to get that value. We don't see questions like that particularly often, especially now, but still they have asked it in the past. And then right after that, question B, the total energy of the satellite when it's at A. So if you couldn't do that, you still should be able to use it in part B. So this has been posted with this assignment. Give them a try. See what you think. These are from old AP exams, but they are, I think, quite relevant. All right, it's good to see you all. Hope you guys have a fabulous day, and I will hopefully see you guys soon. Bye.